Let me continue. So these are two plane fields, and we know that. So let's look at the kernel of dz minus y dx. So dz, we have this rule. Dz del over del x is always 0. So this is one only when we have del over del z. So for this reason, the kernel is technical difficulties. But at the origin, believe me, so this we have a plane generated by these two vectors. Okay, this is a horizontal plane. And when we start to move along this way, you can see positive y-axis now pointing in the, for us, it points in the board. So this is for orientation reasons. And then when we move to -1, so we have this, again, del over del x is this vector, and minus del over del z is this vector. So it is, we have this del over del x minus del over del z and del over del y. So we have this plane. Now, as you can see, the plane starts to twist. So this is actually coming from the non-integrability conditions. To have something non-integrable, the plane has to twist. So when you move along this rate, this y-axis, this, and then the plane twists, when you go to infinity, they twist only 90 degrees. And when you understand this rate, so this is, you see it everywhere. This is distributed all over the tree manifold. As you can see, this is one level, and at, for example, this is the z is equal to 0 level, but at z is equal to 1, you also see the same picture. So this is the contact planes, two plane fields distributed all over the tree manifold. And we have this wonderful theorem of Darboux. So says that all contact structures are locally look like this. So this picture, which manifold do you take? Contact manifold. Locally, they look like this one. And then, yes, we want to study contact manifolds. We want to understand them better. So we look at some submanifolds in the contact tree manifolds, but to understand the special sets for contact tree manifolds are Legendrian knots. But to understand Legendrian knots, we need to understand first topological knots. So these knots we can think knots as a non-self-intersecting closed curve. And then these examples are the projections onto the board. So we can think, okay, we are in R3. So these are the projections. I draw them on the board. So the first one is the unknot, and the second one is the trefoil knot. And this is like, you see, this is like, it looks like a butterfly, but I will tell you which knot is. So, and then we have this this knot table. So this is a table of prime knots. So this we cannot. So this is, they have in the simplest form, and this table is arranged according to its crossings. So we have these are crossings for knots. So up to 7 crossings. We list the knots. So 7-1 means like 7. We have 7-7 means we have 7 different knots containing 7 crossings. And then, like you see, 3-1 is the trefoil knot, and 4-1 is we call it a figure 8 knot. These are like very important ones, figure 8 and the trefoil. You see, there's only one 4 crossing knot. It's the figure 8. Well, this is 3-1 trefoil. We have actually two right-handed trefoil and left-handed trefoil, but they are mirror to each other. So we list them only one of them. We list only one of them here. And then you see this 7-4 knot. Sorry, I don't have a pointer, but this 7-4 knot, you see this is a very special knot. Can you see like there are two hearts become one, it looks like. This is very special knot. It is called endless knot. So it is used as a symbol of Buddhism, actually. So it's like they use it as a symbol of Buddhism. And we have links. So links are disjoint union of knots are called links. We have this simplest link is the half link. And then I just give examples. And we have a Borromean link is a union of 3 knots. And it is also used in mythology. Like if you know the god Odin, this is the symbol of, they say it is Walknut symbol or symbol of power and strength. And courage also. They use it as a symbol. Odin is, I think, their war and that god, they say. I don't say they say it, but it comes from, so the knots are used as symbols also in history. Great. So as it is always the case, when we are studying manifolds, it is very common to study some manifold with nice properties. And for contact manifold, the nice submanifolds are Legendrian knots. So a knot in contact manifold is Legendrian if it is everywhere tangent to the contact planes. So you see, we have contact planes everywhere. And then Legendrian knots are like, they are everywhere contact to these two planes, contact structures, contact planes. And then we also project them onto the board, onto this exact plane. So the projections look like this, but I have to say that these Legendrian knots are still smooth and nice looking, living in the tree manifold, but this certain projections has singularities like this, because since they are tangent to contact structures, so they need to satisfy this condition, z prime minus y x prime should be 0. So when you look at y is, you see it is the slope. So when we can have a horizontal slope, right? This is like a horizontal slope, so it's 0. Y coordinate can be 0, but if you have a vertical tangency, this means that the slope is infinity, but y coordinate cannot be infinity. So that's why instead of these, we have curves. So that's why they look like this. Legendrian knots look like this. Great. So, but given any topological knot, by adding zigzags, we can recover the y coordinates. So we can turn any topological knot into a Legendrian knot by adding zigzags. So there is always a Legendrian knot C0 close to it, in a neighborhood of it. It means that in a neighborhood of it, and this has nice application. So you can always parallel park your car. We will prove this, but I need to say that you or someone can always parallel park your car. So I know some friends, they cannot parallel, they park their car. Maybe 10 years ago, I was also, but now I can. Okay, so we try to model a physical situation here. So XY is let's say the position of a front wheel of a car, and theta is the direction it's pointing, and its configuration space. So we have W is R squared cross S1, And then when we parameterize the motion of the wheel, we have this, the point it's pointing, I mean, the motion is determined by the angle theta. But we can show that, so this psi is a contact structure on W, and whenever we have the gamma t is the motion of the wheel, if and only if we can prove this, parameterizes as a Legendrian curve. So let's look at this theorem in a closer. So if the space is epsilon bigger than your car, we can do this. Okay, let's say that you would like to park your car, and then the path of the front wheel is given as this. So this is the desired path. And we see that this is the motion of a wheel if and only if it parameterizes as a Legendrian curve. But this path is a smooth topological path, right? But we see that we can always Legendrian approximate. So by adding zigzags, we can always make it Legendrian, right? But also in some neighborhood of it, so that it will not cause an accident in this case. So once we figure out the front wheel, so once we put the front wheel in the desired spot, and then we will hope that the rest of the cars also follows. And then, yeah, we will not cause an accident. Here, so you see, contact geometry also have real life applications. And we see that this guy, I can see the Legendrian approximations there. This guy, I'm sure, has a hard time parking. Okay, let's go back to applications in topology. So we have two types of contact structures. As you see, the ones that twist only, like you see, they twist a little, like only 90 degrees when you move towards the infinity. So when you move along the ray, just 90 degrees. But some contact structures twist a lot. So, and they're called over-twisted disk. But how we understand, like, they are over-twisted? So we find the disk. You see, the boundary of the disk is tangent to the contact plane. So we have a special disk. It is called an over-twisted disk. So at the boundary, they are always tangent to the contact planes. And then we know that boundary of disk is a knot, right? So the boundary is a Legendrian knot because it's everywhere tangent to the contact planes. So if you can find such a disk, a contact structure is called over-twisted. If we cannot find such an over-twisted disk, then they are called tight. So in tight ones, there are no over-twisted disks. And then we have two types of Legendrian knots than in contact tree manifolds. They are called loose or non-loose. We look at the complement of a knot. So, okay, you are in a manifold and you have some knots. And then we look at the complement of the knots. And then if there is an over-twisted disk in the complement, the knot is called a loose knot. If we cannot find an over-twisted disk, it is called exceptional or non-loose knot. So if you think about over-twisted contact tree manifolds, you see we have over-twisted disk in this level, but we have every level we have over-twisted disk. So we see the same disks at every level. So for this Legendrian knot, so the boundary of it is a loose knot, right? Because in the complement, it contains an over-twisted disk. It is the boundary of an over-twisted disk is always loose. We see that. But if you have a knot, let's say this intersect with every disk, you know, when you take the complements, so there are no over-twisted disks. They are all punctured. And those are called non-loose knots. And then, okay, we want to like classify and which knots are different or which knots are not same. We want some invariants to distinguish the knots. So these are classical invariants. We have the Thorson-Minnican rotation number. I will define in a minute. And then there are some other invariants we got from Heligard-Floer homology, from contact homology, and we define new invariants from open book decomposition, depth, and tension, or with Ken-Baker we define by using over-twisted disk. The order we define using, again, Heligard-Floer homology. And recently, Etnari and Kegel and we defined contact strategy numbers of this is an invariant of contact structures, but we use Legendrian knots for this one. So I'm not going to tell you in detail, but if you want to know these invariants or how to compute them, you can always find me. I'm here till end of September. I know how to compute loss, but yeah, this is from contact homology. Really, I don't know. Differential graded algebra they use. I don't know about those ones. But
sorry. So given a 3 manifold, I believe that you have probably many ways of having different ways of assigning, I don't know, contact structures. Maybe you were showing different
tight and over twisted.
Yes. So I believe
there are,
for example, can you give these two structures to any 3 manifolds, or how, and what are the what kind of invariants can
these are in R3, but luckily everything looks like this. So for general 3 manifold, as long as you find an over-twisted disk, they are going to be over-twisted. Maybe they don't look like this. The planes doesn't have to look like this, contact planes. But the over-twisted disk is the one that always tangent contact planes along the boundary. So you have the same definition, but they can look different. So these are just examples on R3.
From a contact, so I believe it's probably in the next slide as well, but what kind of information? So I believe that with the contact structure, you can probably get some information about 3 manifolds.
Exactly. So we have invariants, like we can have finitely many types. So we know there are only finitely many tight contact structures on a 3 manifolds, but we can have infinitely many. Once you have an over-twisted, you have infinitely many different over-twisted contact structures. So how we distinguish is we have this invariants, D2 and D3 invariants coming from homotopy theory. So, and then like D2 invariants. And then like say, okay, you have the 3 manifolds. You can have finitely many types. So these are tight ones. And then you can have infinitely many over-twisted ones. And these are all have different D3 invariants. So this is how we distinguish them. I think with Vincent Cullen and Kohonda, they proved there are finite many tight ones. But it's the Eli Ashberg who showed that there are infinitely many over-twisted.
And are these invariants geometrical? What kind of invariants are, what kind of information?
From homotopy theory, they come from homotopy theory. We have formulas to compute them. But yeah, I can't tell you in detail later, but yeah, for S3, they are very easy to compute for S3 and for like length spaces. But once the manifold gets complicated, so the 3 invariant gets complicated. Great. Okay, let's look at the Thorson-Minnican invariant and rotation number. So these are the classical invariants. They are easily computed from the knot diagram. So once you have a knot diagram, we orient the knot, and then at each crossing. So these are the recall, these are the crossings. At each crossings, we can sign a number, plus or minus sign, and then so we sum the number of signs at the crossings, and we minus 1/2 number of cusps. So these singularities are called cusps, and then we just compute the first Dominican from the knot diagram. Like for this unknot, you see it doesn't have any crossings, so the right is 0. And what is the number of cusps? So we have 2 cusps. So this one has first Dominican -1. And then for rotation number, we follow the arrows. So if the arrow goes up, like here, the arrow goes down. So this is a down cusp. And then here, arrows goes up. And the rotation number is computed as 1/2, the number of down cusps, minus the number of up cusps. So in our case, we have 1 down cusp, 1 up cusp. So this is 0. So these are very easy to compute from the knot diagrams. These are classical invariants. And then you see we have to distinguish knots. Okay, we say that these 2 knots are different. They have different classical invariants, but not. We don't need to go there. So this one, first one is an unknot. The second one is a trefoil knot. So its topological types are different. So they are different knots. So we know they are different. We don't need to invariance to distinguish them. But for example, so these 3 knots, they're all unknots. So these are Legendrian unknots. When we compute this classical invariance, so we see that the first L1, the classical invariant of L1 is different from L2 and L3. So we know that these are different. But for these last 2 ones, so we have the same classical invariance. So the question is, when we have 2 Legendrian knots that have the same classical invariance, the question is, are they the same knot or different Legendrian knots? So this is a basic question, classification question. But what do we mean by the same knots or different knots? So this is the formal definition. This is the formal definition. Whenever given at 2 knots, we have a contactomorphism. So this is a diffeomorphism, 1-to-1 onto continuous with a continuous inverse. We want it differentiable with a differentiable inverse. But plus, we want the contact structures. So the contact, it carries the contact structures also. If in this case, let's say, if in this case, if this map takes L1 to L2, then we say, okay, these are same knots up to contactomorphism, or the formal definition is, we said 2 knots are coarsely equivalent. And if this contactomorphism is contact isotopic to the identity, so this means that, what does it mean? We have a map, the map phi, and then we have the identity map from M to N. And then again, it carries the contact structure. So in type T, we go from this map to this map, and every level we also see they are all contactomorphism. They carry the contact structure. So this is stronger. It's also harder because there are contactomorphisms. So we know it's for S3, even for some smallest manifolds like S1 cross S2 or length spaces, I mean, the next step. So we know there are contactomorphisms which are not isotopic to the identity. So it's very hard. Legendrian isotopic classification is harder than the other one. Great, okay, let's look at classification knots. So it starts with 1998, Eliashberg and Fraser classified all Legendrian knots in S3. And in 2015, we also did what we found a method. I will tell you in a second. We find a method that will help us to classify other like non-trivial knots in S3s or also in other tree manifolds. So in 2001 at Naira and Honda, they classified torus knots and figure-8 knots in a tight manifold. Remember, tight ones, they twist a little, over twisted ones they twist a lot, contact structures. What is a torus knot? So this is a torus. You see, torus is, you see in the kids are swimming, it's like a life coat, or how do you say it? Like they use it for swimming. It's not donut. So the donut we eat, you know, the inside is empty here. So donut, the inside is full for the donut. So donut is a tree manifold. So this is dimension 3. But this is the boundary of the donut. You can see that. So this is dimension 2. And the torus knots are knots that we can draw it on this torus without any self-intersection. So these are called torus knots. We can draw it on a torus without intersecting itself. So, and then we have this. This is the meridian of the torus, and this is the longitude of the torus. They are usually, okay, PQ, we say PQ torus knots. So we go P times along the meridian and Q times along the longitude. So like we have a knot, we go P times along the meridian and Q times along the longitude. So these are PQ torus knots. But the simplest torus knot is the trefoil knot. And then we know the figure-8 is the, if you remember from the knot table, it is the only 4-crossing knot. It's the figure-8. And then we study classification results in 3 manifolds other than S3, in T3, S1 cross S2. And then also I have some results in tight length spaces. So S1 cross S2, S3 is like the Superman. S1 cross S2, they say it's a bizarro Superman or something like that, we call it. Length spaces, and so I will tell them what are these manifolds also in a second. And then with this method we found in 2015, so we started to like classify exceptional knots, the knots with tight complements. So exceptional means the knot has a tight complement in various spaces. But the method, like, okay, let me tell you. But to tell you the method and the idea, I need to talk to you about dense surgery. Sorry, I will not go into detail, but what is a surgery along a knot? So this is the topological description. Surgery along the knot. The idea is you remove the neighborhood of a knot and then you glue it back with a different map. So with a different map. But we fix the map. We always, the neighborhood of a knot is the solid torus. It has meridian and the longitude. We remove this neighborhood. And once we glue back, we always glue it with bits going along P times the meridian and Q times the longitude. But if you see, I don't have a pointer, but you see I wrote lambda there and lambda S there. So that longitude, actually we choose, depends. So it comes from the information comes from the knot itself. So this lambda I draw here is for the unknot. So it's for the unknot. But so for the lambda S and the details, I will give explanation next week in the mini course, so I plan to. But I hope you get the idea. We remove the knot, but we put it back in a different way. And this PQ tells me everything. So I don't write every time the map. I just write the knot and that coefficient P over Q to say that, okay, I'm doing this surgery, I'm doing this surgery, I'm doing a surgery along P over Q surgery along the M knot, or I can do it along any knot I want. In this case, trefoil knot. Okay, and then we can see S3s are like we are doing +1 surgery. If you remember, like we did Q mu plus Q lambda, and 1 means P is 1, Q is 1, yeah, or -1, and less spaces, so we get minus P over Q, so it's like minus P mu Q lambda. So this is a LPQ, the length spaces. And then the manifold S1 cross S2, we can think them as the zero surgery, like P is 0 in this case, gives us the S1 cross S2, the tree manifold. You see, I remove something, and when I put it back, I'm in a different universe. You can think it like that. Okay, I was in S3, but now I am in another galaxy or another universe. So everything is different now. The knots are different, everything is different. And we have the contact analogous. We can do surgeries along the Legendrian knot. It's the same, similar, not the same. Similar. Okay, let's go back to the classification of Legendrian knots. So once we have, so we want to classify Legendrian knots in part S3 or over-twisted S3, let's say. And then, okay, let me give you, so how we do it, let me give you the idea. We fix the Thurston-Minnican number. Okay, we say that. Okay, let's say that, okay, I'm just giving you an example. Let's say that we have a Legendrian knot with Thurston-Minnican is equal to 2. So this is a Legendrian knot. So what we do is we find the number of Legendrian knots, so number of Legendrian knots with Thurston-Minnican 2. So we show that it is less than or equal to n. In this case, it's less than or equal to 2, but let's say we are doing in general, let's say TBN. So once we say that, okay, there are at most n Legendrian knots, then what we do is we are explicitly constructing this, and then using surgery theory, we construct explicit and examples of knots. So after this construction, then we know that this must be n, right? So there are exactly n number of Legendrian knots with Thurston-Minnican 2. And then how we distinguish them? We distinguish by then the rotation number differs them, like, okay, there are 2 different Thurston-Minnican 2 ones. So one of them has Thurston-Minnican 2, rotation 1 in this case, and then the other one has Thurston-Minnican 2, rotation -1 in that case. So there are exactly 2 different knots. So this is how we do the classification using. So the method, I mean, we differ from the other result is, okay, this explicit examples makes difference, because we don't say, okay, there exists such knots. Here they are. We also add more information. We show the knots. We give them explicitly, which helps, which has many applications, like constructing counterexamples or classification results. Because when you say, okay, I need TB -6 trefoil knots, Legendrian trefoil knots, and then looking at our classification, okay, here, it doesn't exist in a tight one. Well, it exists, let's say TB0 trefoil knot. it doesn't exist in a tight S3, but from our classification, it exists in over-twisted S3, so we can find them if we need, once we need it. And then, yeah, and then we can apply this idea to other spaces also, but the finding is like finding the explicit presentations are important. So explicitly constructing the knots. So the red knot is like the unknots that we look for. We use surgery theory in this knot. So after the surgeries, after you all done all the surgeries, they are going to give you the desired Thurston-Minnican Legendrian unknot. And then we did the first non-trivial torus knot. And but yeah, I need to emphasize this red curve L looks like unknot, right? But it's a torus knot actually, positive torus knot. But this is when after we done all the surgeries, it becomes a torus knot. Yeah, we see it using Kirby calculus techniques, or it's like not maybe reverse engineering, but once you know like how many at most, constructing that many examples gets easier. But if you construct like n-2, let's say, you found only n-2, but you know there are at most n, then you need to show, okay, like there cannot be two more, like you need some more theoretical things there. They don't exist, so they are only n-2 knots. You need to some other ways to show. Great, yes, Legendrian knots are, so this is why we care about classification, or why we care about Legendrian knots, because we need them to detect, so they detect tightness, over-twistedness. You remember, so the boundary of an over-twisted disk is a Legendrian unknot. So remember the over-twisted disk? So this is an over-twisted disk. Let's say D, and boundary of D is a Legendrian unknot. And then we know how to compute its Thurston-Minnican. It's a Thurston-Minnican zero unknot. Once you find such a Thurston-Minnican zero unknot in a three manifold, you can say, you can conclude, okay, it's over-twisted one, over-twisted. And to distinguish contact structure, we use Legendrian knots. And then for constructions, counterexamples, we use Legendrian surgery a lot. So recently also, Etnayer and Tosun, I think they use it to classify this exceptional torus knot. So the torus knot with tight complement, they use it to classify the tight contact structures on small Seifert tree manifolds. So like small Seifert tree manifolds. We can think them as like surgeries along this link. Let's say we have the coefficients A1, B1, A2, B2, A3, B3. So the small tree manifolds are the result of these surgeries. And then like, again, this exceptional torus knots with tight complements. People use it to construct explicit embeddings of rational homology balls in CP2, and it's blown up. So this is a very recent result, 2023. Okay, maybe I will give a reference. So this is applications to four manifolds. So at Nair, if you want to check out. This is also a recent application. And then, okay, I said, okay, we use to detect topological properties of knots. We can use Legendrian knots like genus, slice genus of a knot. What is a genus of a knot? So this was for every knot bounds a surface in S3. Genus is the number of holes in the surface. Like this one has 2 holes, so genus is 2. And then this doesn't have any hole, right? So this is a genus 0 surface. This is a genus 0, 1. And torus is a genus 1 surface, but so we want the boundary to be a knot. So this is a genus 1. Like, what is the minimal genus for a knot? So the knot has infinitely many Seifert surfaces. These are called Seifert surfaces, the surface that the knot bounds. But there is a unique minimal one. So what is the minimal genus for a knot? For a knot, we can use Legendrian knots to detect. And the slice genus is, okay, we are in S3. But what is the minimal genus if we go to D4? What is the minimal genus that the knot bounds in D4? Like, what is the genus of? So this is the slice genus. Legendrian knots also used to detect the slice genus. Hybrid knots are related to open books, so I will talk them next week. And then, yeah, let me end with questions and open problems. What can we do more? So we classify half lengths recently in S3, also in length spaces. We give also with Hausdorff-Geigers, we give a complete link classification. So first, complete link classification in tight S3s or also in over-twisted S3s. So we did the complete classification. We know everything about half lengths in S3, of course. But what about the next one? So what about whitehead links in contact tree sphere? Okay, we talk about the knots, same or I mean, in our technique, we always classify the same knots. So same, if the Thurston-Minnican and rotation are same, we say 2 knots are always opticon tautomorphism. They are the same, but we have the first example of 2 non-isotopic Legendrian knots in the tight S3 with the same classical invariance. So these are called Chekhov-Eliashberg knots. This is the 5-2 in the knot table. This has 5 crossings. These 2 have same Thurston-Minnican. I think the Thurston-Minnican is 1, rotation 0. They have the same Thurston-Minnican and rotation number, but they are not the same. So these 2 knots are not the same. It is shown by using contact homology. Yeah, this is shown by using contact homology. And then there are examples of, so this Chekhov-Eliashberg knots live in tight manifolds, but also we have some others living in the over-twisted manifolds with a tight complement. So they have the same Thurston-Minnican and rotation number, but they are different. So they are distinguished by using this loss invariant I told you. So they have different loss invariant. Even they have the same classical invariance, they have this different loss invariant. But these knots are constructed as connected sum. So do you remember the knot table? I told you they are prime knots. So connected sum is if you have two knots, let's say K1 and K2. So by this is the connected sum operation. We remove an arc from 2 knots, and then you see that it's like now we have only 1 knot, but we can separate them into 2 different knots. So you see this, it's like 2 knots are connected together. So these are connected sums. For prime knots, like for trefoil, or we cannot separate it into two different knots. So those are prime knots. It's like prime numbers, like, okay, we can write 6 as 2, 3, or we can write it, but 7, we cannot do it. It's like prime knots. And then the question is, but we don't know any non-isotopic prime knots. So prime knots, we don't know any such an example doesn't exist in the in over-twisted contact tree manifolds. And I will tell you the classification of the figure 8 knots is also not known for over-twisted contact tree manifolds. Figure 8 is the 4-crossing one. You see, it's the simplest one, but we don't know even a explicit examples with a tight complement. So it's not known. I mean, I know, but it's not in the literature, yeah. And then I told you about the small Seifert manifolds. So I think the next step, so they are given as the surgery, and then classify anything. One may try to classify any knot types in small Seifert fiber tree manifolds, and this will help, I think, classification of tight contact structures in small Seifert fiber tree manifolds also. Okay, this is all I want to say today. Any questions or? No questions.
Can you say anything about contact topology in 4 manifolds?
In 4 manifolds, so there are no contact structures on 4 manifolds. So because contact structures exist only in odd dimensional manifolds, so you need to have an odd dimensional manifold to have a contact structure. But yeah, once you have a 4 manifolds, and then we know it's boundary, like 4 manifold with a boundary. If you have a 4 manifold with boundary, boundary of X is a 3 manifold now. But in even dimension, we have symplectic structures. So we can look at, once you have a symplectic structure, so what happens to it on the boundary, like we can look at those and then relate those ones. But on even dimensions, we don't have a contact structure.
For example, you can talk about it in 5 dimensions.
5, yeah, because it's odd.
But then you won't have not
like,
unless you do
but you know, we have surfaces like yeah, like, okay, in 4 manifolds we have Lagrangian surfaces, but once you go higher dimensions, we have analogous to like Legendrian knots. Can say.
How would you characterize this? I mean, everybody who comes here, which is basically a knot.
I could, like, the loops, like, you know how they connected to labs. You right? It's like a closed loop. It's like a path. It's a knot. Yeah, I can knot or link, you know. Exactly, yeah, it's doable. It's doable, yeah. Like, okay, without going to lab 3, how can I go to the other labs? It's definitely a topological problem. We can solve it, yeah.
So you had that, well, you had the definition of like a contact homomorphism, right? And
Contact homomorphism.
but for that, the domain and the codomain were the same. But could
Yeah.
you sort of modify that to tell if Legendrian knots in different contact manifolds are equivalent?
But no, because you need to like a diffeomorphism. The manifold should be the same. So
Yeah.
But if the manifold is different, so this has to be M1. So you need to go. You cannot go to M2.
Oh.
This has to be M1.
So like even if L1 and L2 were both like the trefoil and you had one of them in R3 and the other one in S3, you wouldn't be able
No,
to say
but
they're equivalent?
but yeah, S3 and R3, the special case, like if you remove one point from S3, they are contactomorphic to each other. And then in that case, it doesn't, I think they are the same because you can remove the one point from the two knots, away from the two knots. But I understand your question, like if I have a length space or S3, but in that case, they are still related because the length spaces are like p-fold covers of, they are still somehow related. Just you need two different like, okay, S3 and small private manifolds, like something not related. But still you cannot, I mean, they are like you are we are on Earth, they are on Mars. So they are completely different. We can breathe here, there are no atmosphere there. So completely different worlds. But the question is, okay, I am here, another manifold. Can I go there from using Legendrian knots? So this is an interesting question. Okay, I do surgery here. Can I go to Mars, other planets? Can I do it? This is the classification results says you can do it or not by just like, for example, in the Poincare homology sphere, this is, we know that, is this negative? This is there is only one way to, this is a special manifold, let's say 3 manifold. There is only one way to get the Poincare homology sphere. It's the -1 surgery along the left-handed trefoil knot. And then like, okay, I want to go from S3 to this word in a contact setting. So can I find the Thurston-Minnican something? Thurston-Minnican 0 left-handed trefoil in the S3. So we can answer these questions. In type 1, no, we cannot. So we cannot go to other planets. But if you are over-twisted, oh, I can go it. Yeah, I can do it. It's so interesting and different. Like you have parallel universes, even for S3, like so many parallel universes, you can like it's the quantum jump from one to another. Can you do it? Or just in one operation?
Okay, thank you.
Yeah, thank you. Thank you very much.